All right, let's do some circles review. So we're going to start by going over the major theorems that you might want to know for circles. I've tried to narrow it down to the ones that are going to come up the most often, and then we're going to do a ton of example problems of all different types. So starting with this, let's look at these sort of big 9 theorems that we're going to have. So the first one is finding the sector area, and so there's 2 different ways to do this. The first is to think about a circle as a whole 360 degrees and a sector as a piece of that. And so what you can do is the angle over 360, or the part over whole, equals the sector area over the whole area, which is pi r squared. So some teachers will show you this way to do it. The other way to do it is to say, okay, a whole circle is area pi r squared, and I only want theta out of 360 degrees of that. So again, that's thinking about, let me pick another color, theta as that angle right in there, and we just want the area of this sector. So this says find the whole area, and then this is the fraction of it, right? Theta over 360. Or we can do part over whole and set it up as a proportion. Now the same thing will work for arc length, except instead of just trying to find the sector area, we're trying to find a piece of the circumference. So now I'm saying find the length of this part of the circumference, and I'm still going to call that theta. So again, 2 ways you could do this. You could say part over whole equals arc length over 2 pi r, because 2 pi r is the entire circumference, which is the whole length around. Or you could say I'm going to do theta over 360, because that's my fraction, times the circumference, the entire circumference. So take that fraction of the circumference. But again, 2 ways to do the same exact thing. Different teachers will show you different ways. All right, center radius form, especially converting into center radius form. You want to have x minus h squared plus y minus k squared equals r squared. And I want to go through one example on this because there are some tricks that I use that can help you if this is something you get stuck on. So let's say I have x squared plus y squared minus 4x plus 12y minus 1 equals 0. So the first thing I'm going to do is I'm going to group my x's together, leave a space, group my y's together, leave a space, and add the constant to the other side. So that would just be positive 1 over there on the right side. Now I'm going to complete the square. And I don't just call it that for fun. I do it because I actually draw a little square here. And we're making a perfect square trinomial. So I'm going to divide that middle term by 2, square it, making sure to keep that in parentheses. And then I'm going to add that number squared right there, completing my square. So you can see it actually makes like a little square there. If you draw on that square, it helps you remember every step. Now, whatever I do to one side, I also do to the other. So I'm also going to add 4 over here. Same thing with the y's. I'm going to take half of this. I'm going to square it. And I'm going to add that in right here. And again, whatever I do to one side, I do to the other. So this side will just add up to be 41, combining those 3 things. But this actually, drawing the little square, helps me here because what I see now is that factoring this will always be the same thing. I'm always going to take this variable and this number. So this will be x minus 2 squared plus, same thing here, this variable and that number, y plus 6 squared. And so my center is at 2, negative 6, change both your signs, and my radius is the square root of 41 because that's r squared over there. And again, we'll do some more examples with that, but that's just one quick one. All right, inscribed angles. An inscribed angle looks like this. It has its vertex and these 2 endpoints touching the circle. And the inscribed angle is always 1/2 of the intercepted arc. Okay? And the way that I have my students kind of figure this out is I color in the angle, that's my inscribed angle, and look at which arc gets inscribed there. So if this was 50, this would be 25 degrees. The next one, intersecting chord. So a chord goes from one side of the circle to the other. It doesn't necessarily need to go through the center, although a diameter is a chord. And so here we've got two intercepted arcs. We've got this intercepted arc and that intercepted arc. So when I find the measure of any of these angles here, I'm going to find it using those two intercepted arcs. So here, because these meet in the middle of my circle like this, I always have my kids put their arms up in that cross shape and then turn it. Oh, that looks kind of like an addition sign, right? That looks kind of like an addition sign. So this is 1/2 the sum of the arcs, arc 1 plus arc 2. So again, on the circle, it's just half the arc. When they're inside the circle, it's half the sum of the arcs. And then when they're outside the circle, it's half the difference. So I think about these two secants or tangents meeting outside the circle, right? I'm going to color that in to find my intercepted arcs. And so my intercepted arcs are this one and this one. And I always say to my students, because they meet outside the circle, that kind of looks like a subtraction sign, right? So this is 1/2 arc 1 minus arc 2. So when they meet outside the circle, it's half the difference. So Miss Krogman always says this, and I love stealing this from her. So this is in, out, on. And then this is half. This is half the difference, or the sum, sorry. And this is half the difference. So think about in, add, out, subtract, on, leave alone. Okay, now let's talk about lengths. So intersecting chords and their lengths. So let's say I have two chords that intersect, and they break each other up into parts. Let's call this A, B, C, and D. And notice A and B are part of this chord, C and D are part of the other. The relationship we have is that A times B equals C times D. So for example, if this is 2 and 5, right, and that's 3 and x, I could say 2 times 5 equals 3 times x. Now, intersecting secants or tangents. Here's the phrase I want you to remember. Whole times outside equals whole times outside. So, in a problem like this, the whole is this whole thing. The outside is just this part. The whole here is this whole thing. The outside is just that part. In another scenario, like where we have a secant and a tangent, then I could say the whole is this. The outside is just that. But on the tangent, the whole is this, and the outside is that. So those are the same lengths. All right, and then the last big thing that is often forgotten is this, that if I have a circle and I have a radius and I have a tangent, that is going to form a right angle with the tangent, okay? So that comes up often. Often we'll get right triangles. There are a lot of other circle theorems, but these are sort of my big 9 that I've narrowed it down to. So these are the 9 I would focus in on as you study. Okay, so let's get into some examples, and we're just going to do a ton of different examples tonight. So starting with this one, the equation of a circle is this. What are the center and the length of the radius? So I'm going to do what I just practiced before and convert this into center radius form. So I'm going to group my x's. There is only one. I'm going to group my y's, y squared minus 6y, and then leave a blank. and I'm going to move my constant to the other side. So the x's are already a completed square. I don't need to do anything with that. The y's, I'm going to take the middle term, take half of it, square it, and add it to both sides. Whatever I do to one side, I also do to the other. So this right side is going to equal 8. The left side is going to be x squared plus, now I'm going to take this variable and this number, y minus 3 squared, and this is my standard form of the circle. So my center now, I'm going to switch the signs, is 0, 3. So that lets me eliminate 2 and 4 and 3 actually. And then my radius, well, r is going to be the square root of 8, which is the square root of 4 times 2. Square root of 4 is 2, so that is 2 radical 2. So that is answer choice 1. All right, next question. A circle whose center is the origin passes through the point negative 5, 12. Which point also lies on the circle? There are 2 ways to do this. Well, let's talk about both. So the first way that I would say is to figure out the radius and then determine which one of these also are on that radius. Because if I have a circle and I know that this point is on the circle, I know that I have a given radius from the center. And whichever other point I choose should also have that same radius, right? Whatever this is should be the same as that. So if we did it that way, we know my center is at the origin. So thinking about this, I'm going to find the distance between 0, 0 and negative 5, 12. So that would be negative 5 minus 0 squared plus 12 minus 0 squared, which is the square root of 25 plus 144, square root of 169. So that is 13. So what I would need here is for my radius to be 13. So I'm going to pick these points, and I'm going to see if the distance between the center, which is 0, 0, and that given point is 13. And if it is, they should be the same. So let's try the first one. So I'm going to say that this is the square root of 10 minus 0 squared plus 3 minus 0 squared. I can already tell you this isn't going to work because this is the square root of 100 plus 9. That is not 169, so it's not that. Now number 2, this would be the square root of 12 squared plus 13 squared, not 169, so not that. The next one is the square root of 11 squared plus 2 radical 12 squared, and you can just put that in your calculator. That is 1 square root of 169, so it is this problem, or that answer. Now the other way you could do this is you could say that you know that this is x squared plus y squared equals 169 because this is r squared, right? This is r, remember? And then you could plug each answer choice in and see which one has that as its output. But I would say checking your radii is probably a little easier. All right, next question. In the diagram below, these are radii, and AB, BC, and AC are drawn. Which statement is always true? Is BAC congruent to BOC? This is not true because BAC is inscribed, BOC is central, so BAC is actually half of BOC. The next one, BAC is half of BOC. This is true. That is the definition of that is the measure of an inscribed angle. So that one is true. So the answer should be 2. Now, I don't know anything about the areas because I don't know the lengths. And are they both isosceles? Well, I know this one is both radii, so I know that one's isosceles. But I don't know anything about these lengths. Remember, this isn't necessarily drawn to scale. So it could be that this is the central angle, and then these really are like this, where this one is much longer than that one, not necessarily drawn to scale. So I don't know that one, even though it might look to be true. Okay, next one. What is the area of the shaded region? So, first of all, let's find the angle measure of the shaded region. A whole circle is 360. So if this is 60, that means the shaded region is 300 degrees. So now, again, there are two ways you can do this, and I'll show you both ways. The first is to set up a proportion, part over whole equals the sector area over the area of the whole circle. And then you can cross multiply that. The other way to do it is to say, well, this is the area of the whole circle, and I want to take this fraction of that and just multiply it through. So either of those setups will work, but when you do that, you should get answer choice 4, which is 160 over 3 pi. And notice this is in terms of pi, right? All right, next one. This is another sector area. We're trying to find the area of sector COB, so that whole sector. And I notice that this is 108 degrees. So let's think about how we would do this. So it's 108 degrees out of 360 degrees. So I see that these two fractions are right, but the question is, are the other two? So if you do 108 over 360, you actually get 3 over 10. And so that is totally fine. So these could all be right. Now, I know that I want that part of the whole circle. So what I need to figure out is, well, which one of these are radii? So let's match these up. So BC is this. That is not a radius. So I'm going to eliminate Amy from my answers because BC is not a radius. So 3 is out and 1 is out. Now Beth says OC, pi r squared. That is a radius. So because of that, Beth could be right, so both of those answers are still okay. Now Carl says that the radius is half of AB. Well, AB is the diameter, so half of that would definitely be the radius. So that is how I know that this is right. It is not Dex because Dex says take AB, square it, and then take half. So Dex's order of operations are off. All right, let's go to the next one. The graph below shows AB, which is a chord of circle O. The coordinates of the endpoints are 3, 3, and 3, 7. The distance from the midpoint to the center of circle O is 2. So let's find the midpoint of AB first. And you can just guess and count. Or we could do midpoint formula, 3 plus 3 over 2, 3 plus negative 7 over 2. And so that comes out to be 3, negative 2. So my center is right here. And they tell me that that is 2 units from the center of my circle, which means the center of my circle is either here or here, because those are 2 units from that midpoint. Now, does that help me eliminate any answer choices? Well, this would be at 1, negative 2, and this would be at 5, negative 2. So let's see. This answer choice 1 would have a center of 1, negative 2, so maybe 1. This would have a center of negative 5, positive 2, so not that. This one would have a center of 1, 2, not 1, negative 2. And this one would have a center of 5, negative 2. So it's got to be 1 or 4, just based on the centers. So now let's take a look at this. The real distinguishing factor here is going to be the radius. So here's what I know. If this is a chord, I know that, let's say this is my center. The circle would have to go around, that is not a great circle, but go through A and B. So I know that my radius would either go from here to B, or from here to B, or from here to A, or from here to A. And so I'm going to figure out the length of that radius, and I'm going to use that to help me determine which equation is right. So you can do this with distance formula. I'm actually going to do it with Pythagorean Theorem, just because we haven't done that yet. So I'm going to turn that radius into a right triangle. This is 2, this is 5, and 2 squared plus 5 squared equals r squared. So this is 4 plus 25 is r squared, and so that tells me that 29 is r squared, so this must be answer choice 1. That's a pretty difficult question, right? It takes a lot of deductive reasoning in there. All right, let's go to the next one. BC is the diameter of a circle. Which statement must always be true? So BCD, point D is somewhere on here. BCD is a right triangle. That does have to be true because this is 180, which would make my inscribed angle 90 degrees. Again, by 180, I'm referring to that arc. BCD is an isosceles triangle. Don't know. Doesn't always have to be true. They are similar triangles. I don't know enough. They are congruent triangles. That's, again, I don't know enough. So it's got to be 1 because this 180 degrees and the inscribed angle is half the arc. Okay, let's do another one. So in this, we've got all those segments and we've got chords drawn. FD is a tangent. So when I think tangent, I think T, I think right angles. Okay? So I already know if it's a tangent to the radius, I'm going to have a right angle right there. Sam decides to apply this theorem. An angle inscribed in a semicircle is a right angle. What angle is he referring to? Okay, so which angle is inscribed on a semicircle? So my semicircles that I see are either this one or this one. Which one of those has an angle inscribed on it? Well, right there, that touches on the semicircle, but that's this angle, and that's not inscribed on that arc. So it's not going to be that. Now I've got this one. Now look at this. This is inscribed perfectly on that semicircle. So I'm looking for that angle. Okay, let's see if we see that. So either BCD or DCB. So I see that it's this. But the other way you can do this is actually to test them out. So AOB, that's this option, right? So let's actually trace that. AOB. That is not necessarily making a right triangle there because it's not inscribed. BAC. BAC is this. That's not inscribed on a semicircle. DCB, that is inscribed on a semicircle, so we know that's right. And FDB, yeah, it's a right angle, but it's not inscribed on a semicircle. So that's how I know it's 3. All right, next problem. So for my next one, what is the area of a sector of a circle with a radius of 8 formed by the central angle measure of 60? So same kind of problem, right? The whole circle is pi r squared. We're talking area, right? And the piece I want is 60 out of 360. Or you could say 60 over 360 equals x over pi r squared. Either way, you're going to wind up with 32 pi over 3. All right, a designer needs to create perfectly circular necklaces. The necklaces each need to have a radius of 10. What is the largest number of necklaces that can be made from 1,000 centimeters of wire? So if I'm talking about a necklace, I'm talking about circumference, right? And so what I need to do is figure out how many circumferences I can get from 1,000 centimeters. So I know that my radius here is 10. So my circumference here is 2 pi times 10 or 20 pi. Now, how many necklaces can I get from 1,000 centimeters? So I'm going to do 1,000 divided by 20 pi, and that gives me okay, next one. What is the area of the area of the shaded sector is 2 pi. If the length of NL is 6, what is the measure of angle N? All right, the length of NL is 6, which means that my radius here is 3. And I want to know the measure of angle N. So I notice that N is inscribed. And so if I could figure out this central angle measure, that would be half of that because it would be half of the arc. So let's start with this. And I'm going to use a proportion for this just because that's the way I happen to do it. You can do it other ways. But I'm going to say, okay, the angle over 360 equals 2 pi over pi r squared, which is 9 pi. So the part of the area over the whole. So I'm going to solve this. So this would be 720 pi equals 9 pi times theta. Divide both sides by 9 pi. And so that would give me that theta equals 80 degrees. So that means the central angle is 80 and this arc is 80. So angle N is only 40. Now you could also set it up like this. You could say theta over 360 times pi 3 squared equals 2 pi and solve for it the same way. But I think cross multiplying is a little bit easier to solve here. But again, it doesn't matter what you do. All right, next one. Which statement is not always true? Knowing that we've got chords here. So let's start with the ones that I see are true. So first of all, I know that these are congruent because they're vertical angles. And I see that this arc right here, this angle and that angle are inscribed on that same arc, which means that this and this would be congruent. And the other thing I know is if two angles are congruent, well, guess what? The third have to be also. So let's start with what that tells me. That tells me that CEG and FDG have to be congruent. So that must be true. It also tells me the triangles are similar by angle-angle similarity. So now the question is, well, which of these are true? Does CG have to be congruent to FG? Well, I know that these are similar, but I don't know that they're congruent. So let's look at what the next one says. The next one says that CE, this, over EG, this, equals FD, this, over DG. Those are corresponding parts. So this is true because similar triangles, which means that one must be the one that's not necessarily true because the triangles are not necessarily congruent. All right, let's go to this one. The equation of a circle is this. What is the center and radius? So x, we just did, no we didn't. All right, x squared is alone, there's nothing else with it. Y squared plus 6y blank. And the 7 is actually already on the other side. So the x's are good. I'm going to complete the squares for the y. Divide by 2, square it, add to both sides. And so I know that this equals 16. So already I actually can eliminate 3 and 4 because I know that that's r squared, so I need the square root of that. So now let's figure out the other part. So this is just going to be x squared plus y and 3. So this is y plus 3 squared. Change your signs, and so this would have to be answer choice 2. Next question. Same idea. What are the coordinates of the center and the radius of this? X squared minus 4x blank plus y squared plus 8y blank equals negative 11. Complete the square, that's negative 2. Square that, it is positive 4. This is 4. Square that, it's 16. And so this is 9. This is x minus 2 squared plus y plus 4 squared because this is x and minus 2 and y and positive 4. So my center is at 2, negative 4. So not these two. And my radius is the square root of that, which is 3. All right, next question. A circle with a radius of 5 was divided into 24 congruent segments. So this is 5. I can also say that is 5, that is 5, right? And that is 5. So I'm kind of just labeling what I know. The sectors were rearranged as shown in the diagram. So let's look at this. This length is really half a circle, right? and that's the same as this because we're just expanding it out. And so that's the same as this. So what is the value of x? Well, x is half of the circumference. So the circumference is 2 pi r. So that's half of 2 pi times 5, or 5 pi, because my 2's would cancel. 5 pi is approximately 16. That's a very strange question. Okay, next problem. In this circle, OA is 4, AB is 5, PC is 10. What is BC? So let's do some corresponding parts here. So 5 corresponds with x, and 4 corresponds with 10. So this would give me 50 equals 4x. So x equals 12.5. All right, next one. All right, let's go to this one. In the diagram below, quadrilateral ABCD is inscribed in a circle. What is the measure of angle ADC? So this angle is what I want to know. Now, here's the theorem you need to know here. In any cyclical quad, a quadrilateral inscribed in a circle, angles across from each other are supplementary. They add to be 180. So 72 plus x has to equal 180. So x would have to equal 108. Okay? Opposite angles are supplementary in any cyclic quadrilateral, which is a quadrilateral inscribed in a circle. All right. What is the area of the sector formed by FOH? We've done a bunch of sector area here. So again, 2 ways to do it. Either do, let's see, we know that FH is congruent to OG. And I know that this is a diameter, so that's also congruent. And this is another radius, so that's congruent. So this is equilateral, which makes this angle 60 degrees. So I'm going to do 60 over 360 times pi r squared, or I can do 60 over 360 equals x over pi r squared. Either of those setups would work for this problem. And so I get for my answer 6 pi. All right, only a couple more. Yeah, we're not going to do all of these, but let's do a couple more. So in this one, tangent DA, secant DBC are drawn. Arc AC is congruent to arc BC, and BC is 152, which means AC is 152. What is the measure of angle D? Okay, so this whole triangle, or this whole circle, needs to add up to be 360. And if each of those are 152, that's already 304. So 360 minus 304 is 56. So now we're trying to find the angle. So I'm going to look at what my intercepted arcs are. My intercepted arcs here are AB and AC. So I'm going to do 1/2 of 152 minus 56 because they meet outside the circle, so that looks like a subtraction sign. So 152 minus 56 is 96. And half of that is 48 degrees. All right, let's look at the next one. So AE and BD are tangent to circle O and P at AE, B, and D as shown in the diagram. That's going to be really important here because they're tangent from the same point. So what I actually already know is that this segment and this segment must be congruent, and this segment and that segment must be congruent. So AC to CE is 5 to 3. So this is like 5x, and this is like 3x, because they're in that ratio. And BD is 56. Determine and state the length of CD. So here's what I know. I know that this piece is congruent to that piece, right? and that this piece is congruent to that piece, that means the whole segments are congruent by segment addition. So what I know here is that 5x plus 3x must equal 56. So 8x is 56, and so x equals 7, right? 56 divided by 8. So to find the length of CD, well, I know here that CD is congruent to CE, so I'm going to do 3 times 7, and that is 21. Okay, probably about 2 more. Let's see, let's skip those. All right, this next one, Dominic thinks that angles A and B have the same radian measure. State where Dominic is correct or not and why. Now, we can do this a bunch of different ways, but I think at this level, at your comfort level with radians, the easiest thing to do is to not try to mess around with radians as much as let's work with degrees. So what I'm going to do is I'm going to find these angle measures in degrees, okay? And then we're going to go from there. So I know here that my arc length is pi, right? I know my arc length is pi. And I know that that's a section of my whole circumference. So what I know is that I'm going to have A over 360, part over whole, is pi over the whole circumference, which is 2 pi r. So I know A over 360 equals pi over 8 pi. So 8 pi times A equals 360 pi. Divide both sides by 8 pi. So A equals, the pi's cancel. So I'm just going to do 360 over 8, which is 45 degrees. So angle A is 45 degrees. Using arc length, right? Now I'm going to do the same thing for B. So B over 360 equals the part of the circumference over the whole circumference, which is pi times 6.5 squared. Or I'm sorry, that's area. 2 pi r. 2 pi times 6.5. So when I cross multiply, this gives me 13 pi B equals 13 pi over 8 times 360. Divide both sides by 13 pi, and I get that B equals 45 degrees. So, is Dominic correct? Well, I would say yes, since the angle measures are equal in degrees. They will be equal in another unit, such as radians. They are equal in radians. Again, there are other ways to do that. I've seen people take ratio of pi to 4 and then do the ratio of 13 pi over 8 to 6.5, and that comes out to be true, so that works, okay? So there's lots of different ways to do this, but I think converting into degrees is an easier way to look. All right, last question for circles review. During an experiment, the same type of bacteria grow in 2 petri dishes. Petri dish A has a diameter of 51, which means I know I might need a radius of 25.5. And Petri dish B has a diameter of 75, which gives me a radius of 37.5. I also know the population in each after 1 hour. Population density is population per area. So for Petri dish A, that would be 40,000 over pi times 25.5 squared. For Petri dish B, it would be 72,000 over pi times 37.5 squared. Now let's determine which of those is actually bigger. So calculating those out, and I'm not rounding here, I'm going to have that Petri dish A has a population density of 19.58066962 bacteria per millimeter squared. and Petri dish B had 16.2974617 bacteria per millimeter squared. So those are my two population density. Which has a higher population density? It would be Petri dish A. All right, again, if you need more construction practice, that's in my other video. And that's about it. All right, let's do one last one. Below is find the area, or the area of the shaded sector is 12 pi. The length of OA is 6. What is the measure of AOC? So two ways to do this. Either the angle over 360 equals the part over the whole area, which is pi r squared. Or you can do the angle over 360 times pi r squared equals the area of the sector. These will get you the same answer either way. I'm going to solve this one over here on the left. So this would be 36 pi x equals 12 times 360 is 4320 pi. Divide both sides by 36 pi, so x equals 120 degrees. And you get the same answer that way too. All right, if you have other circle questions, send me your thoughts or your questions. Circles are not a major part of the test, but every single question we did on this paper is a test straight off a Regents. And this link document is on my teacher site, as I said in the beginning of the video. So let me know if you have any other questions, and have an awesome day.